This morning and today, actually. So it is my pleasure to present for this last talk to Luca Vitagliano from University of Salerno, and he will speak about integrating Nijenhuis structures. But before we start, just a sec, I would like to make an announcement. After the talk of Luca, we will take a picture outside the building. So please, after he finishes his talk, just stop there for a sec, so there will be a picture. You'll show your friends that you will take a picture in La Casa de Papel. So whenever you want.
Thank you very much. So thank you very much for the invitation. So this is my first conference in person after more than 2 years. And actually, this is my first Poisson conference, so I'm very, very happy to be here. I think that the organizers are doing a great job, so thank you very much. Okay, today I will report on joint project with two colleagues of mine in Salerno, Fabrizio Pugliese and Gianni Sparano, and yeah, the keyword is Nijenhuis structure. So let me start recalling what a Nijenhuis operator is. I'm sure that most of you already know, but just to fix things. So given a manifold, a Nijenhuis operator is a 1-1 tensor satisfying an appropriate integrability condition. Before discussing the integrability condition, let me mention that I will often interpret 1-1 tensors as vector-valued one form. So this is often useful. And then the integrability condition is just the vanishing of the Nijenhuis torsion of the 1-1 tensor. The Nijenhuis torsion is a vector-valued one form which is defined, by this combination of the 1-1 tensor and the commutator bracket on vector fields. And actually, it can be also defined via the Fröhlicher Nijenhuis bracket of vector-valued one forms. It's just half the self-bracket of n. These Nijenhuis operators appear every now and then in geometry. Often they appear in relations with other structures, particularly interesting for this conference. They often appear in relation to Poisson structures, but they also appear, in their own. So here is a short list of instances. For instance, complex structures are actually Nijenhuis operators of a specific kind. So an almost complex structure is just a 1-1 tensor satisfied the complex identity. So it's a fiber-wise complex structure on the tangent bundle. If it's additionally a Nijenhuis operator, then it's a genuine complex structure. Another class of examples that will play some role in this talk are the so-called integrable almost tangent structures. These are special G structures which are specified by a 1-1 tensor satisfying this identity. So the kernel coincides with the image, and in the integrable case, when the Nijenhuis torsion vanishes, then we say integrable almost tangent structure. The reason for the name is that the standard example of this guy is the vertical endomorphism in the tangent bundle. As this vertical endomorphism will also appear somewhere else in the talk. Let me remind now what it is. So on the tangent bundle of a manifold, I will describe this locally, okay? So we have standard coordinates like x, x dot, and then the vertical endomorphism is the 1-1 tensor locally given by this formula. But actually, this is independent of the coordinates and really gives you an integrable almost tangent structure on the tangent bundle of any manifold. And actually, every integrable almost tangent structure is locally of this type.
Luca, why does it give minus identity instead of identity?
This is a complex structure.
So it's another.
Yeah. So another instance that I will also discuss later from my point of view is projections. So projections in the geometry are just 1-1 tensor satisfying the projection identity. So this means that the kernel and the image, I mean the tangent bundle splits as the direct sum of the kernel and the image of the projection. In the integrable case, we say integrable projections. For instance, flat Ehresmann connections in a fiber bundle are instances of integrable projections. And there are more exotic, Nijenhuis structures that are sometimes considered in differential geometry. In principle, you could study 1-1 tensors satisfying any polynomial identities. For instance, for appropriate choices of the polynomial, we get what people call metallic structures, and in the integrable case, you call them integrable metallic structures. Okay, this is just to make another example. But as I mentioned, these Nijenhuis structures do also appear in connection with Poisson structures and related structures. Already in the very classical work of Magri Morosi on Hamiltonian systems, they appear as recursion operators in B Hamiltonian systems. This means that you have a Poisson structure and a Nijenhuis structure that interact nicely. In that case, you get, for instance, a full hierarchy of Poisson structures on your manifold. And in this case, you talk about Poisson-Nijenhuis manifolds. For instance, holomorphic Poisson manifolds are special instances of this situation. When the Poisson structure is non-degenerate, it's a symplectic structure, you usually call these things symplectic Nijenhuis, and for instance, holomorphic symplectic are instances. And you can also generalize. So there are some works on generalizing Poisson-Nijenhuis structures in the direction of Dirac geometry. For instance, there is a work by Clemente Gagliardo and Joana Nunes da Costa, and more recently, Enrique Burstein, Drummond, and Netto proposed a definition of what does it mean for a Dirac structure and the Nijenhuis tensor to be compatible. So they have a theory of Dirac Nijenhuis structures. Okay, but in the last years, Boltsinov, Konyaev, Matveyev initiated a program which basically aims to studying Nijenhuis structures in their own. So forget about possible identities satisfied by the 1-1 tensor or possible interaction with other structures. Just study a Nijenhuis tensor in its own. And actually, they already found several interesting results. For instance, they have some local normal forms theorems that resemble the classical splitting theorem in Poisson geometry. They also discuss linearization. They also have a bunch of applications to Poisson, Nijenhuis geometry, and so on. Maybe, some of you might remember the talk by Boltsinov at the Global Poisson last January. Well, actually, at the end of the talk, I think that Rui Fernandes asked the question whether this Nijenhuis structure had a group-like object attached to them. The question is motivated by the fact that every Nijenhuis tensor actually gives rise to a Lie algebraic structure on the tangent bundle. So if you have a Nijenhuis tensor, you get a Lie algebraic structure here, which works as follows. So the anchor should be a map from the tangent bundle to the tangent bundle, and it's just n itself. While the bracket it should be a bracket on vector fields, and it's just this kind of deformations of the usual commutator of vector fields. For instance, when n is the identity, you really recover the plane tangent bundle as a Lie algebroid, right? So if, as there is a Lie algebroid, it's natural to wonder whether, this Lie algebroid is integrable. When is it integrable? And the case in the case when this is integrable, if there is some additional structure on the Lie groupoid which is responsible for the origin of the Lie algebroid from a Nijenhuis operator. So I interpreted the Ruiz question in this direction, and in practice, this talk answers, provides a possible answer to Ruiz question, basically. And actually, everything will be partly analogous to what happens in Poisson geometry. Well, you know perfectly well what happens in Poisson geometry, but let me remind anyway. So forget for a second about Nijenhuis structure and just take a Poisson structure on a manifold. Then we are in a similar situation because the Poisson structure induces a Lie algebroid structure, but now on the cotangent bundle, right? The standard cotangent Lie algebroid. So in this case, the anchor is given just by the sharp map of the Poisson structure, and the bracket is the usual Kosul bracket on one forms. And one of the remarks that actually triggered the contemporary way in which we work in Poisson geometry is that if this Lie algebroid is integrable, then on the source simply connected integration, there is an additional structure which is responsible for the Lie algebroid coming from a Poisson structure. We all know this very well. This is just the multiplicative symplectic structure on the Lie groupoid from the now classical works of Weinstein and Karasev. For those who are not familiar, omega is a symplectic structure on the Lie groupoid, which is multiplicative in the sense that it satisfies appropriate compatibility with the Lie groupoid structure. So this is the situation in Poisson geometry that we all know. So it's natural to wonder whether there is a similar picture just for Nijenhuis geometry. This is precisely the spirit of the talk. So now forget about Poisson, just look at Nijenhuis geometry. So on one side, we have a Nijenhuis manifold. This gives rise to a Lie algebroid that might or might not be integrable. But in the case in which it's integrable, the question is, what do we get on the global side? So is there any, so let me say it again. So is there any structure on the Lie groupoid which is responsible for the Nijenhuis operator on the infinitesimal side? Yeah, do you have questions so far?
In the Poisson case, the symplectic structure and the induced Lie algebroid structure are compatible, no? In the sense that they form a bialgebroid, no? And I was wondering whether if, in this case, this structure that you gain in the tangent, what is the compatibility? It's easy to explain the compatibility with the classical.
I didn't get which compatibility you are
referring to? When you have a Poisson structure, you gain a Lie algebroid structure on T star M.
Right.
But this is compatible with a symplectic structure you have there.
So you're only looking at the infinitesimal picture, right? In this question.
Which is the only thing you have for now, no?
Okay. Well, actually, the very last part of the talk deals with this question, basically answers this question. So is there any compact description of Nijenhuis operators in terms of structures on the Lie algebra which are compatible with the Lie algebroid structure? Yeah. Is this the question?
Yeah, maybe.
Yeah. Okay.
No, I was saying you have two structures on TM, no? The classical one and the one induced by the Nijenhuis.
You are asking about the compatibility.
Exactly.
The compatibility is just. Okay, let's put it like this. On the shifted tangent bundle, okay, this is a little bit aside, but let me answer. So on the shifted tangent bundle, when you have a Nijenhuis operator, you actually have two DG structure. You have two homological vector fields, the standard de Rham differential and a differential coming from the Nijenhuis operator. And the compatibility is just that these two homological vector fields commute. Does this answer your question? Okay. Okay, so the other questions? No. Okay, so the plan of the talk is like this. So, well, I will need to discuss multiplicativity in the realm of 1-1 tensors, and I will do this in the first part of the talk. In the second part of the talk, I will state my main integration results. So I will discuss what is the structure on the Lie groupoid responsible for the Nijenhuis operator. It will be really very easy. I just need one slide to explain this once I explain what a multiplicative 1-1 tensor is. And in the last part of the talk, I will discuss examples, hopefully interesting. Well, this is complementary, so if I will have time, I will discuss this. Otherwise, I will just leave it aside. Okay. So let me begin with multiplicative tensors. So this will play a role in the picture. I will only work with the multiplicative 1-1 tensors. So again, multiplicativity of a geometric structure on a Lie groupoid means compatibility with the groupoid structure. And the original definition of multiplicative 1-1 tensor is due to Laurent Jangoux, Stienon, and Xu in their paper on integration of holomorphic Lie algebroid, I guess. And recently, Enrique Bursten and Drummond widely generalized the definition to tensors of any type, basically. But I will only need 1-1 tensors, actually. So begin with the Lie groupoid, then you all know that you can take the tangent prolongation. So TG is also a Lie groupoid with objects Tm. And now take a 1-1 tensor on G. Again, I will often understand it as a vector varied one form on G. And we say that T is multiplicative if when you understand T as a map from TG to TG, then it's morphic in the sense that it's a Lie groupoid map. But there is an easy way how to construct examples which works like this. So take the Lie algebroid of G, and now take a one form on M with values in A. I will denote it U. Okay, so locally, you can, well, even globally actually, you can always factorize U like this as a sum of tensor products of one forms and sections of A. And now you can promote U to 1-1 tensors on G, at least in two ways. So there is this way, which I call U right invariant, which consists in taking the target pullback of the theta I and the right invariant vector fields associated to the alpha I. And then there is this guy, which I call U left invariant, which consists in taking the source pullback of the thetas and the left invariant vector fields associated to alphas. So these two guys are now multiplicative, but this combination is multiplicative automatically. I denote this guy like this, delta U, because of the following. Actually, the multiplicativity of 1-1 tensors is a cocycle condition. So there is a complex which is responsible for this notion. Well, I will not go into details, just a few details. So this complex, so there is a canonical complex which is concentrated in degrees above -1. So in degree -1, this is degree -1 piece, you have A valued one forms on M. In degree 0, you have, just the 1-1 tensors on G. And in higher degrees, you have more complicated stuff. But now, a 1-1 tensor on G is multiplicative if and only if it is closed with respect to this differential. And actually, this construction, which I presented in the previous slide, is precisely the definition of the first arrow in this complex. So this guy is automatically multiplicative. In some sense, this is the cohomologically trivial case. Well, for instance, there is this curious example. Of course, there is at least one canonical multiplicative 1-1 tensor on any Lie groupoid, which is just the identity of the tangent bundle, which is trivially multiplicative, which means that there is a canonical class in this complex, in this degree, and actually this class has a geometric interpretation. You can prove that this class vanishes if and only if G integrates the tangent bundle. So might be, I don't know, might be like the pair groupoid or the fundamental groupoid, any groupoid integrating the tangent bundle. Okay. Questions about multiplicative 1-1 tensors? No. Okay. Okay, it's complicated to describe in few words, but let me mention that this is like a close cousin of the deformation complex of a Lie groupoid. You just replace like points in the nerve with points in the tangent of the nerve, basically. Otherwise, it looks very much like the deformation groupoid, the deformation complex, sorry. Okay. Yeah, and now I'm ready to present the main result. It's just one theorem describing when does a Lie groupoid integrate the Lie algebroid of a Nijenhuis operator. So the theorem states that this is the case if and only if the following condition is satisfied. So there must exist an A-valued one form on the base satisfying two conditions. The first condition is a non-degeneracy condition. So first, the dimension of G should be twice the dimension of M. This is an obvious constraint. But then the rank of U right invariant should be the same as the dimension of M. And the second condition is an integrability condition, basically saying that U right invariant is itself a Nijenhuis operator on the Lie groupoid. Well, actually, there is an equivalent version of this condition, which is this one. So U right invariant and delta U, the multiplicative vector field, should Fröhlicher Nijenhuis commute. Well, this is useful because actually in the infinitesimal picture, we have a very similar situation. And actually, the way how did we guess this statement is first looking at the infinitesimal picture, using DG manifold to describe the infinitesimal picture, finding a theorem like this, and then guessing that the global picture should be the same, or similar, say. Well, under these conditions, you also have that delta U is itself Nijenhuis, and in this case, it contains a full information on the Nijenhuis operator downstairs, because N is just both the source and the target projection of delta U. And you also have control on the actual isomorphism, Lie algebroid isomorphism between the Nijenhuis Lie algebroid and the Lie algebroid of G, because U, the one form U, is what provides the isomorphism. Okay. Well, in some sense, this is similar to what happens in Poisson geometry, but it's also very, very different from what happens in Poisson geometry. The main difference is the following. While in Poisson geometry, we could only guarantee the existence of the multiplicative symplectic structure on the source simply connected integration, well, surprisingly, in this case, we have this U, this U, this U right invariant, this delta U on any integration, which surprised me at the beginning. I do not have an explanation, just some vague thought. Okay, this is the main result. Do you have questions? Yeah.
About the rank, is it maximal rank?
No, it's not. No, it's not maximal rank, it's half maximal, right? Because the dimension, so this is not at all invertible. So right, this is just half.
Maximal satisfying those equations or some properties?
Well, let's put it like this. This is the best approximation of an almost tangent structure, on an almost tangent structure on the groupoid. Yeah. Yeah, I'm not sure if you can put like your suggestion, like maximal rank satisfying certain properties. I don't know. Okay, so let's come to examples. First, the trivial examples, the two extreme examples. I mean, you may have the zero Nijenhuis operator or the invertible maximal rank Nijenhuis operator. So in the zero case, the algebroid is trivial, so it's just a zero bracket and zero anchor, right? So, which means that it is integrated by, well, a very simple Lie groupoid. It's just a copy of the tangent bundle with the source and target both coinciding with the tangent bundle projection, and the multiplication just being the fiber-wise addition in the tangent bundle. In this case, U, it's just the identity. And then you can prove that U right invariant and U left invariant are just the vertical endomorphism of the tangent bundle, which I've already mentioned, and its opposite, so that delta U is actually 0. This is in agreement with the main statement because the projection of 0 is 0. So the projection of delta U should be n, and this is 0. Good. The invertible case is also trivial. This is the case, for instance, for a complex structure or for a metallic structure. In this case, the anchor of the Lie algebroid is actually an isomorphism of Lie algebroid. So we know up to isomorphisms, we know everything about this Lie algebroid. So we know what are their integration. For instance, this Lie algebroid is integrated by the pair groupoid. And indeed, we have all these Nijenhuis structures on the pair groupoid. In this case, well, U is just n itself. Then U right invariant is just n in the first component and 0 in the other component. Similarly for U left invariant, and delta U is just n plus n, basically. So n in both components.
Sorry, in your theorem, you have this U, which is a form on m with values in A.
Right.
So it doesn't see the groupoids at all. Is it the case that it's always defining, and when there is a groupoid, you have the other?
Yeah, U, you always have U. U, it's just U, it's the idea, well, yeah, U in a certain sense, it's just the identity. I mean, if you have n, then you want to have a map from Tm to the algebroid, which in this case is just a deformed version of Tm. So in this case, use just the identity. So you always have.
Yeah, fine.
Yes?
Also, regarding this extract of the group, have you tried of seeing it as a BV groupoimorphism from the tangent to itself or something like this?
This U?
Yeah, as part of
Well,
something.
delta U is multiplicative. So this can indeed be considered as a VB groupoimorphism from the tangent from TG to TG.
But so is delta U determining U? Maybe this is a question.
No, delta U does not determine U.
Okay.
So the true ingredient is this one.
Okay. Thank you.
Sorry?
But just one more thing. You can think that you have like the adjunct or representation on A, and U is like a form with coefficients in the adjunct representation.
What do you mean by abstract representation? Joint representation.
Because that's also what it seems behind the complex that you were describing.
Yeah, I cannot answer the question, but well, it wouldn't be surprising if the adjoint representation is involved, as long as the tangent groupoid is involved, right? So the adjoint representation is just a manifestation of TG, and here TG plays a major role because, yeah. But yeah, I cannot say much more than this. So, yeah. Yes.
Can you not write the second condition just in terms of U?
The second, in terms of U,
Yeah, not the.
yeah, of course you can. So there is a notion of Nijenhuis torsion for these guys, and then you can write the second condition in terms of the vanishing of this algebraic Nijenhuis torsion.
Which is like being close for the adjoint.
Maybe. Okay, thank you for the remark. I hadn't talked about this. Yeah. Okay. Yeah, good. Thank you. More questions? No. Okay. So the next example is, integrable almost tangent structures. So the question is, so let's take a Nijenhuis operator, which is additionally an integrable almost tangent structures, and let's try to see whether or not it's Lie algebroid integrates, and then what you get on the integration. Actually, to make it simple, I only considered the canonical example of an integrable almost tangent structure, namely the vertical endomorphism of the tangent bundle. So now, in this example, I assume the manifold being the tangent to something, to some base manifold B, and N being the vertical endomorphism, as I already wrote in local coordinates. It looks like this. And actually, in this, topologically easy case, you can describe explicitly the Weinstein groupoid of this Lie algebra. So first, this Lie algebra is integrable, and you can describe its source simply connected integration. And this is curious because this gives kind of exotic Lie groupoid structure on the double tangent bundle, as I will show you in the next slide. But first, I need to remind you something about the double tangent bundle. So the double tangent bundle is actually an example of a double vector bundle. So there are two vector bundle projections from TTB to TB. One is just the tangent bundle projection, projecting a vector to its base point, while the other one is just the tangent, the differential of the bundle projection of TB. And these two projections gives to TTB the structure of a double vector bundle. In coordinates, the maps look like that. And another structure that I will need is the canonical involution. So there is a canonical involution of TTB which swaps the two vector bundle structures that in local coordinates look like that. Okay, and now I'm ready to describe the source simply connected integration. I don't want you to read, to follow all the details. I will just say a few things. So I want to integrate this Lie algebroid. This is the Lie algebroid of the Nijenhuis operator, when the Nijenhuis operator is the vertical endomorphism of the tangent bundle. Well, in this case, the space of arrows is another copy of the double tangent bundle. The source and target are interesting. These are just the first projection. So maybe I didn't insist on the notation, but I'm denoting by tau the tangent bundle projection, and by tau prime the differential of the projection downstairs. Okay. So the source in this groupoid is just the difference of the two projections, while the target is the sum of the two projections. And it's a little bit harder to describe the multiplication, but you can do this in local coordinates. There are formulas. And you can prove that this is indeed the source simply that this is a Lie groupoid, and it's the integrating this Lie algebroid. You can do this by hand. Well, the way in which we found these formulas is really, describing A paths up to A homotopes. You can describe explicitly the isomorphism between the original Lie algebroid and the Lie algebroid of this groupoid. Okay, I do not want to insist on this, but let me briefly discuss all the Nijenhuis structures on this integration. So according to our main theorem, there is a left invariant, right invariant and left invariant Nijenhuis operator, and there is a multiplicative Nijenhuis operator. Well, the right invariant one is just the kappa invariant part, or maybe better to say this first. So remember that G is just another copy of TTB. And this is a tangent bundle, so it comes with its own vertical endomorphism, which I denote by VG just to distinguish from the previous one. And now the right invariant Nijenhuis operator on this guy is just the kappa invariant part of VG, while U left invariant is the kappa anti-invariant part of VG, and delta U is just what you get applying to VG the involution, and this is actually projects onto V under the source and the target in agreement with the main theorem. Okay. Second example, it's integrable projections. So I mentioned already, projection is a 1-1 tensor satisfying the projector, say, identity, and it is integrable if it's a Nijenhuis operator. So in the integrable case, well, the kernel, well, first of all, as I mentioned already, the kernel and the image form a direct sum decomposition of the tangent bundle, and additionally, because of the integrability, they are involutive distributions. And just for simplicity, I will assume that the image is a simple involutive distribution, meaning that the Leaf space is a manifold and the projection is a submersion. So in practice, the image is just the vertical bundle of a submersion, of a surjective submersion pi. So here B is the Leaf space. With this assumption, the kernel becomes a flat Ehresmann connection in this fibration, which I will denote by H in the next slide. And P is then just the vertical projection with respect to this Ehresmann connection. Okay. And now I want to describe, well, the Lie algebroid of P, and if possible, also an integration, if it exists. As I mentioned, if P is an integrable projection with simple image, I denote by H the kernel. Well, the first obvious remark is that as a bundle, this is just the fiber product of M with the tangent bundle downstairs. So it's the pullback, the pullback of the tangent bundle downstairs to M. Okay. And actually, I need a remark. Before describing the Lie algebroid of P, I need an easy remark that the vertical bundle, so the one which is depicted in red here, this one, actually acts canonically on the horizontal bundle via the usual Bock connection, right? Which works like this. So the covariant derivative of a horizontal vector field with respect to a vertical vector field is just the commutator projected horizontally. So this is a version of the standard Bock connection in the normal of a foliation. Okay. And why do I need this? Because it turns out that the Nijenhuis Lie algebra, so the Lie algebra associated to the Nijenhuis operator P, in this case, is canonically isomorphic to this semi-direct product. If you describe this product as this fiber product, then the isomorphism maps a tangent vector to M into, its P projection and its pi projection. And this is very easy to prove. But now, so this is a semi-direct product Lie algebroid. So it's obvious that the integration should be searched into semi-direct product Lie groupoid. So the idea is first integrating a T pi m and then just taking the semi-direct product with H. Well, and actually you all know that TPM integrates, for instance, the smallest Lie groupoid integrating is just the submersion groupoid, which is the subgroupoid of the pair groupoid consisting of the fiber product of two copies of M. And actually the Bock connection, so in this case the Bock connection integrates. So there is an action of the submersion groupoid onto the horizontal bundle, which works like this. So an arrow here is just a pair of points in the same fiber, in the same pi fiber. And if you take the horizontal space here and the horizontal space there, they identify, because they both identify with the tangent space downstairs. And this identification is precisely the action of the submersion groupoid on the horizontal distribution. So you can take the semi-direct product, and this will automatically integrate the semi-direct product, this semi-direct product, which I remind you was just isomorphic to the Lie algebroid I'm interested in, right? So now I have an integration of this Lie algebroid, and I only want to describe all the Nijenhuis operators on it. Well, and this can be done. I don't want to give details, maybe just delta U. So the tangent to the Lie groupoid, in this case, is just these fiber products. So a tangent vector to G is just a triple, a tangent vector to M, another tangent vector to M, and then a tangent vector to TB. So delta U takes a triple and maps it into this triple. So you project V along P, you project W along P, and the third component is just 0. And this, this is the full story about this case. Do you have questions about the first two examples? No. Okay, so let's discuss the third example. So the two previous examples were regular. So in both cases, the Nijenhuis operator was constant rank. So let's make a non-regular example. It's already a remark of Bolzino, Konyaev, Matveyev that linear Nijenhuis operators on a vector space are the same as what is called pre-Lie algebras. So let me explain this correspondence. So I begin with pre-Lie algebras. So a pre-Lie algebra, well, there is also another name for these guys. They're also called the left symmetric algebras. What is it? It's a vector space, which I denote. So this is meant to be a fracture A. So it's a vector space fracture A equipped with the bilinear product, which I denote with this triangle, which in general is not associative, but the associator is symmetric in the first two entries. So this long formula is just saying that the associator of this product is symmetric in the first two entries. Okay, let's make examples to convince you that this definition makes sense. So, well, associative algebras are pre-Lie algebras in a trivial way, because in that case, the associator is just 0. Another interesting case is when you have an affine structure on a manifold. So this means a flat and torsion-free connection on a manifold. In this case, you can put a pre-Lie product on vector fields. The pre-Lie product in this case is just given by the covariant derivative. this the name Preely algebras come from the following remark that the commutator defined by the Preely product is actually Lie bracket. So there is an underlying Lie algebra for every Preely algebra, which I denote by fracture A Lie just to distinguish from A. Well, for instance, in the associative case, this is just the commutator Lie algebra of an associative algebra. In the case of an affine manifold, the Preely product commutator is just the usual commutator of vector fields. And actually, this Lie algebra comes with an additional structure, which is that of an action on the vector space A itself. And the action is given by just the Preely product. And actually, the Lie algebra with this action know everything about the Preely algebra. In particular, we have an integration theorem for Preely algebras. So in the case of finite dimensional real Preely algebras, actually, there's a one-to-one correspondence with the simply connected Lie group equipped with a left invariant affine structure. That's why I consider this example, because in some sense it's universal. Good. And what has this to do with Nijenhuis operators? So begin with a finite dimensional R vector space. So forget about Preely product for a second. Then a Nijenhuis operator on, A, it's a manifold, right? It's a very simple linear manifold. And the Nijenhuis operator on A is called linear if in linear coordinates it has linear coefficients. So these objects here are actually constants, okay? And Boltsinov, Konyav, Matveyev remarked that actually there is a one-to-one correspondence between Preely products on the vector space A and linear Nijenhuis operators on A. It's easy to describe this correspondence in terms of these constants. So if you begin with the product and you take its structure constants, then this guy is automatically a Nijenhuis operator, which is additionally linear. And conversely, if you begin with a Nijenhuis operator, which is linear, these coefficients are the structure constants of a Preely product. Well, more intrinsically, the Nijenhuis operator of the Preely product can be described like that. So at the point x, it must take a tangent vector at x to a tangent vector at x. But now A is a vector space, so a tangent vector is just another point in A. And the image is just given by the Preely product again, up to a sign. Well, this proposition is interesting because it's a kind of a Nijenhuis analog of the Lie Poisson structure on the dual of a Lie algebra. So Lie algebras are the same as linear Poisson structures. Lie brackets are the same as linear Poisson structures on the dual, and this is the analog in Nijenhuis geometry of this result. And actually, the general discussion about the integration of linear Poisson brackets has an analog in this Nijenhuis geometric picture. So in order to explain this, maybe so I know that you are very, very expert, but let me discuss the Poisson case first, okay? So if you have a Lie algebra, then on the dual, you have a linear Poisson structure, the Lie Poisson structure, right? And then you wonder whether this Poisson structure is integrable or not, looking at the cotangent Lie algebroid. Actually, it turns out that the cotangent Lie algebroid is canonically isomorphic to the action, to the coadjoint action Lie algebroid. And then you can integrate like this. You first take the, well, say for instance, the source simply connected integration, the simply connected integration of G, and then you can take the cotangent groupoid, which is actually canonically isomorphic to the coadjoint action groupoid, which is an integration of the original linear Poisson structure. And the picture, I mean, we have a very similar picture in the Nijenhuis geometry realm. So let me give you a little bit, some more details. So begin with the pre-Lie algebra, take its Nijenhuis operator, and remember that the underlying Lie algebra acts on A, so you have the action Lie algebroid. And actually, it turns out that the Nijenhuis Lie algebroid, so the Lie algebroid associated to N, is canonically isomorphic to the action Lie algebroid, and the isomorphism is just the identity, when you describe TA as the product of two copies of A. As a consequence, any Lie groupoid integrating the action Lie algebroid does also integrate, is also an integration for the Nijenhuis operator that you were looking for. For instance, you can take the source, the simply connected Lie group integrating A, and in this case, the Lie algebra action integrates to a Lie group action on A, so a representation of G on A, which I call beautiful L, and of course the action groupoid integrates the Nijenhuis operator, and it only remains to describe the Nijenhuis operators on the integration. I don't want you to follow the formulas. The point here is that there are explicit formulas for U right invariant, U left invariant, delta U, and of course everything fits with the main theorem. How much time do I still have? 7 more. Okay. Do you have questions about the examples? Yes? Sorry?
Leibniz algebra is an example of...
Leibniz algebra, as you said.
Yeah. Pre-Lie algebra? No.
I don't think so.
Oh, thank you.
Thank you. Maybe it's a silly question, but regarding this example of the projection, no,
right.
This Nijenhuis that equals its square. Before the integrability condition, it's as if having two complementary distributions, no?
Right.
And how the integrability condition reflects on these distributions? Is it the same?
They're both involutive. I think.
It is the same?
But this is not equivalent. There is also compatibility between the two distributions, I think.
And then in this case, when you integrate, can you relate, I don't know, the monodromic groupoids or of these two foliations somehow?
Honestly, I don't know. I haven't thought about this.
Okay.
Thank you for the question. More questions? No. Okay, maybe I have some minutes to go a little bit deeper into the infinitesimal picture. I like this part of the picture because actually this is what we started with. So we first looked at the infinitesimal picture, and then we guessed what should we have at the global level. So what we did is just describing Nijenhuis operators in terms of DG manifolds. We were inspired by the situation in Poisson geometry. So let me remind you the situation in Poisson geometry. Given a Poisson manifold, well, Poisson manifolds are actually equivalent to what we call degree 1 symplectic NQ manifolds. So degree 1 NQ manifolds means a DG manifold which is concentrated in degree 0 and 1. And the symplectic means that it is additionally equipped with a degree 1 symplectic structure which is compatible with the homological vector field, in the sense that the homological vector field is Hamiltonian. So there is a one-to-one correspondence given by the shifted cotangent bundle construction, which is due to Reutenberg. In this case, the symplectic structure is just the canonical on the cotangent bundle, and the homological vector field is the Lie algebroid differential of the cotangent Lie algebroid. Okay, and the question is, do we have a similar picture in the Nijenhuis geometric case? The answer is yes, but to explain this, I first need to explain what is an infinitesimal multiplicative 1-1 tensor. Again, the original definition is due to Laurent Jean-Gustien and Shu, but then Bursin-Drummond for tensors of any type. So infinitesimal multiplicative is like the infinitesimal version of multiplicative, right? And this means that you have a geometric structure on the Lie algebroid which is compatible with the Lie algebroid structure. In the 1-1 tensor case, this means the following. So we have a 1-1 tensor on A, the total space of a Lie algebroid, which is also morphic when seen as a map from TA to TA. So remember that TA is itself a Lie algebroid over Tm. And if T respects the structures, then we say that it's infinitesimal multiplicative. And this is really the infinitesimal version of multiplicative in the sense that if you apply the Lie functor to a Lie groupoid with a multiplicative tensor, you get a Lie algebra with an infinitesimal multiplicative tensor. And again, the infinitesimal multiplicative condition is actually a cocycle condition. So you can define a complex responsible for this notion, and the complex works like this. So begin with a Lie algebroid and shift by 1 the fiber degree. You get a DG manifold. This is a standard correspondence between Lie algebroid and degree 1 DG manifolds. And then you take the following cochain complex. So the cochains are just 1-1 tensors on these graded manifolds. And the differential is just the Lie derivative along the homological vector field. This complex can be described, for instance, in low degrees. So it's concentrated in degrees above -1. In degree -1, actually, 1-1 tensors can be described as A-valued forms on M, while in degree 0, they can be described as linear 1-1 tensors on A. So these are 1-1 tensors on the total space A, which satisfy an additional linearity conditions, which means an appropriate compatibility with the vector bundle structure. So just the vector bundle structure, not the Lie algebroid structure. And now, infinitesimal multiplicative tensors on A are precisely 0 cocycles in this complex. And again, there is a canonical class which vanishes precisely when A is the tangent bundle, the usual tangent bundle, with its canonical Lie algebroid structure. Okay, and now let's relate Nijenhuis operators with DG manifolds. So I begin with describing with a trivial thing, describing when a vector bundle is the tangent bundle. So this can be done in terms of graded manifolds as follows. So an isomorphism of a vector bundle and the tangent bundle is actually equivalent to the following graded object. It's the same as an almost tangent structure on A shifted by 1, which is of degree -1. And actually, the isomorphism is, identifies the this 1-1 tensor with the canonical vertical endomorphism on Tm shifted by 1. So in this sense, all degree 1 almost, well, degree -1 almost tangent manifolds look the same. They are all vertical, I mean, they're all tangent bundle, shifted tangent bundle with their vertical endomorphisms. Okay, and now let's put a Nijenhuis operator into the picture. So it turns out that the Lie algebroid is isomorphic to the Lie algebroid of a Nijenhuis operator if there exists such a degree -1 almost tangent structure satisfying an additional integrability condition, which can be written like this. So now this is not independent anymore from, it's not equivalent anymore to this condition. So it's really a different condition, since that U and delta U Fröhlicher-Nijenhuis commute. And in this case, you can reconstruct M from delta U just taking the projection. And actually, so you see, this statement is really similar to my main result, especially when you understand this condition in these terms. And this is precisely the way how did we guess this statement. We first proved this, and then we guess this, and then we prove that. Okay. So now, of course, this is just preliminary, right? And now the natural outcome is that maybe you can. It's late. Okay. Okay. Sorry. So that's all. Thank you very much. Sorry for being late.
Thank you, Luca. So, final questions or remarks to Luca? Oh, Cedric has said.
Yes, so I think in Poisson geometry, the way you come across symplectic groupoids is by starting from this basic question: do you find symplectic realizations?
Right.
And then among them, you find the best one.
Right.
So is there an analog of that question? And I'm asking because to me it looks like there may be such a question, and the answer is that there are many interesting possibilities, and you are looking the simplest one somehow. But anyway, do you have the analog of this question?
No, so this is in my open problems list.
What about the analog of Poisson groupoids?
Well, this would be Nijenhuis groupoid. Well, Drummond studied Poisson Nijenhuis groupoid. Now you just put the Poisson structure to 0, and you get. So the analog of a Poisson groupoid should be a Lie groupoid with the multiplicative Nijenhuis operator. I think this is part of Drummond's work on Poisson Nijenhuis groupoid. But I'm not sure that in the paper he specializes to this case. But
I think he talks about the holomorphic case, probably.
Sorry?
I think he does talk about the holomorphic.
I don't hear.
I think he does talk about the holomorphic case, which is.
Right.
But then his analog of your U, does it still go from Tn to A, or is it a map from A to Tmn?
Say it
Do you
again.
remember?
So which?
Your U was an isomorphism between Tmn to A.
To A, yeah. No, the direction is important. It's really a map from Tm to A, not the other way around.
Because I would expect something growing from the other way around and not to be an isomorphism. So does that arise in Tiago's picture?
I don't remember.
Okay, something.
No, so
to
the
study
reason why you
first.
really have this direction is because this is the -1 degree part of the complex controlling this this thing.
I have a couple questions. One is, when you look at the algebroid, this Tm with the Nijenhuis operator, that you put the Nijenhuis operator there. Somehow the Nijenhuis operator is the anchor, right? The anchor is already the operator, which kind of suggests that if, when you integrate that and you look at source and target going to M cross M, right? Somehow this should encode what you want in a way, right? Just because if you differentiate this map, you get exactly N, which is the anchor. I was just wondering if you ever thought about this point of view.
Honestly, no. But I agree that, yeah.
And the other question is if you ever considered the problem of understanding when they are actually integrable.
No, this is another item in my open problem list. So specializing the Crank-Fernandez obstructions to this special case, yeah.
Yeah, because it looks like because you can scale these Nijenhuis operators, a very simple example would be just to consider the identity Nijenhuis operator scaling down to 0. And if you look at all the symplectic groupoids, you'll be getting a family that goes from the pair groupoid to Tm.
Right.
Which looks a bit like, which looks like this deformation space is this cone tangent.
Yeah, that's interesting.
So there could be like interesting families of integrations.
I agree. No, I haven't done that yet.
So, is there any other question, either in chat? No? Oh, Rui.
So, I mean, one of the reasons I asked in the global Poisson the question was to do these linearization results that they have in I think it was a bit still preliminary, the results that they had, but now that you have these formalism, first, so if you have a Nijenhuis structure that vanishes at a point, you have like a linear approximation. Assuming everything is integrable, can you reproduce their linearization results?
I didn't try. This is one of the items in my open problem list. So this is really
but this doesn't look like,
things.
I mean, I think you have everything in place, so it doesn't look like very difficult.
I agree. I still didn't have the time to look into details. So. But I agree that once you have this machinery, in principle, you can solve all the problems in Poisson geometry that you usually solve using the integration. They have an analog in Nijenhuis geometry, so just use this machinery to deal with them. Yeah, and hopefully one recovers Bolzino, Konev, Mathieu.
And I think they also had some cohomology classes appearing there they were not really Lie algebroid cohomology classes for these Lie algebroid, but they had some cohomology classes in the talk that I cannot
honestly, I don't remember now.
You don't? Okay.
Yeah, I don't know.
But it may be worth to, I don't know.
No, I agree.
Review the talk and redo all the results that they have and probably finish the results because it wasn't complete.
I agree. That's definitely worth. Yeah,
okay.
Sure.
Thank you.
Thank you.
So,
Yes, thanks, Luca, for the talk. So, my question is, in this future problem that I put you put very fast, what is the role of the linear Poisson structure associated with the Nijenhuis Lie algebroid? You have the Lie algebroid with the Nijenhuis structure, and in the dual.
Yes.
In the dual bundle, you have a Poisson, a linear Poisson structure. You can take the advantages of this.
Yeah, you asked me this question already, and I actually, sorry, I didn't have the time to think about this.
Yeah. Okay.
But I've thought about the Poisson Nijenhuis case, the two groups, so we can discuss later if you like.
Yeah. Okay. Okay. Thanks.
Thank you.
Okay, so there are no more questions, so I think we can thank Luca again. Thank you very much. And remember that now we have the picture outside. Thank you.